Hi everyone, this is Dr. Sheets. Today I'm going to talk about Chapter 9, Database Design. In this chapter, we talk about how systems are developed, how information systems are developed. They're developed for the purpose of taking some data, manipulating that data, aggregating it, slicing, dicing, who knows, and presenting it to the users and giving them user interfaces and reports and providing them information for their decisions. This process that we go through to develop a system is called the systems development lifecycle. And databases fit within that lifecycle and have sort of a parallel lifecycle about how they're developed. And so that's what we're going to talk about today. And then some about how to take a conceptual model and turn it into a physical model. Well, the database has to fit within the information system it is developed for. And we do that by matching our design to the world, like we've said in ER diagramming. And so we're going to learn about that along with the systems development life cycle, the database life cycle, how we transform our conceptual designs, because remember, that's where we actually have the solution to the problem, and then how we turn that into the physical design, which is the actual implementation within the database. So, and with that, let's get started. Well, an information system provides our abilities to manage all of our data, to bring together the people, the hardware, the software, the programs, the procedures, the policies, everything that we need to create this information system that we need to help us solve some problem or issue within our organization. It's a system analysis that looks at the situation and decides whether we need the system and what the system is going to do. Systems development is how we create the system, the series of phases and steps within those phases that we use to actually develop the system. This is exactly the idea that you learned about in your software engineering class in ACIS5504. It's just sort of a little overview or summary of that material. Like sometimes a little extra reminder doesn't hurt. Plus, I like the idea of putting this class in the context of other classes that you have had. Well, so applications are what we develop. I mean, that's how we create information for decision makers. We have reports, we have user interfaces, we have tables that we present. What we do to create an application is we have the data that it processes, and then we have the program that takes that data and puts it into a form that a user can use it in a useful way. So here's sort of the idea, just at its like highest level, where we have some data, we have our program, and that our program applies procedures, loops, ifs, sums, other things to create a report or visual representation that can be used to make decisions. And pure and simple, that's what an information system is. Well, the performance of our system, which is sort of what we're interested in as we get further along in the process, right? I mean, when we started our semester, we weren't worried too much about performance, but now it's starting to creep into our thinking as we learn the tools and techniques for designing and implementing databases. Now we want to start to think about optimization. And I don't think it will be hard for you to know that performance matters. About the time you sit in front of a web page for 17 seconds, you'll be annoyed, and you'll get the point that it's not easy to use a system that doesn't perform well. And so performance really matters. And in our world, your design can really make a difference. The design of your database. If you have a poorly designed and implemented database, you can make it more difficult or you can make your performance slower than it would have to be if you had a correctly designed database. Of course, you won't be doing that because you're following our ER model, relational, and foreign key structures. But we'll see here in a couple of lectures about how easy it is to create a query that will take much longer than an equivalent query or similar query. And you'll see what your application does, how you write the program makes a lot of difference in how well your system will perform too. And then there's a whole bunch of administrative procedures that you might do at the end of every month in terms of organizing the data on the disk and things like that to prepare for the next month that we actually use something like that to impact performance in at Department of Energy for our billing system. And so performance is important. You're going to have to monitor it. You're going to have metrics to keep track of it, and you're going to want to do things to improve it. Well, so database development is similar to the systems development. It's the process of getting the data right, and we use ER modeling to do that, to get the solution right and the design right. And then in implementation, what we do is we create the actual database and then load it with existing data, and then begin our processes of backing up and managing the data in an organized, reliable way. Well, here's sort of a summary of the systems development life cycle. I mean, it consists of 5 phases: planning, analysis, detailed systems design, implementation, and maintenance. And it's not really perfectly sequential like it seems, because every now and then you might have to circle back around on one of these things. Like you do some analysis and then you realize you might need some more planning and things like that. What you try not to do is be down here in the implementation phase and have to go back up to the analysis phase too often. That's less than ideal. And it's just a way of thinking about the process of developing an information system. Here's a nice little diagram that sort of summarizes it. Right? We start out by planning to determine, is this something that we want to do? Is it something that we can do? Then we move on to understanding, well, the user requirements. What processes do they need to do? What data are they going to produce? What data are they going to use? And this is the place where we solve the problem. When we get below this point, the solution is known. And so now all we have to do is take that solution and translate it into the form of the database, and then write the programs and things to implement that design. Right? So here we have the solution by the time we get to the end of this phase. Now, in this detailed system specification, what we do is we go into great detail about everything that we need to do in the system. Not only do we, in the analysis phase, we know all the use cases. We know what the user has to do. But in the design phase, we're going to say we're going to have a user interface for this use case. And this user interface is going to look like this. and it's going to have it's going to get this data, it's going to produce this data, it's going to read rows from this table or select rows from this table, and it's going to insert row into this table. And so all that stuff is perfectly written in the detailed system specification phase. Now, there's some other methods out there like Agile and things where these approaches aren't followed, but still, I think this is more common, and you can see we have a chapter or an appendix on object-oriented analysis and design, which is similar but slightly different. Anyhow, so you come out with a detailed design spec that has everything in it that you need for implementation. So now you know exactly what to do, so then you start writing your code. In your code, your database has to be there first because your programs are going to be accessing the database, and then you test, and test. Testing is much more important than I ever realized before I got into industry. Testing is really important. And then once you've released the system and it becomes operational, then you are into a maintenance phase where you're always evaluating performance, seeing if you need to improve performance any. You have maintenance to do to adjust to new business requirements or other enhancements due to technology upgrades or things. So this is sort of the basic idea or a way of looking at how a system is developed. Well, so planning happens at the company level. The plan is there's a planning committee, and that committee decides which projects are going to be done. And what they do is they review the projects in terms of their business values. So they then decide what projects need to be done. And so when you are looking now at a particular project, usually there's some existing system, and you ask the question, what should you do? New requirements come along, the old system is no longer perfectly doing what it needs to do, what should you do? Should you continue it, or should you modify it, or should you make a new system? And if you're going to replace it, are you going to make a new system, or are you going to try to buy a new system? What are the actual hardware and software requirements? What will be the system cost? Look at possible alternate solutions. And then, so what you have is you have the situation of you have an operational cost right now of the existing system. Presumably, because it requires workarounds and other things to adapt to requirements, it costs more to operate than it used to. And the question is, can you design, implement, and operate a new system such that the operating costs of the new system pay for the system's costs through lower operational costs than the pre-existing system? So this is sort of the idea of planning. It's sort of deciding what to do, and then what are a couple possibilities of doing it, and then can we do it? The feasibility analysis is the most important aspect of the planning phase. Well, so analysis is where the problem is really solved, right? You understand the problem as completely as possible. You develop an ER model. You develop process models like data flow diagram. Maybe you do UML diagram instead and do swim lane analysis or something like that for your to make sure you have all the necessary processes defined. Then you always take a look at the existing systems. The existing systems have many requirements that the users don't remember embedded in their software. So you should always look at those existing systems, and that'll help you to understand some requirements that users might not really remember or express completely, because every user has their own perspective on what has to happen, their own vision of the problem. And so it's important to be able to understand those different visions and be able to support them. And so our goal is to understand everything that our system needs to do, identify and eliminate any problems, take advantage of opportunities. It is important that we solve only the problem that is really needed. Now, the more elegantly or more generally we can solve the problem, the better. But this is where we are looking to match our model to the way the world works. Well, detailed design is when we take the answer that we come out of with analysis and then make a computer design, a program design. So where we have an application that consists of several different programs. Each program has multiple modules. Each module is made up of multiple components, right? That idea of what is the program structure going to look like, right? Because our program could have a million lines of code or hundreds of thousands anyway. So we have to think about what the structure of what that program is going to look like. So, and then we also want to explicitly say, this is how we're going to get from the old system to the new system. What data needs to be converted, all kinds of steps along the way. And then, of course, all these things have to be approved by management. Well, once our design is approved, right, then we can move into the actual development of the system, which is implementation. And it's sort of a cyclic process of coding and testing and coding and testing. And eventually we get to the point where we've implemented all of our system. Of course, the database, the DBMS has to be purchased and installed and the tables all created before we can begin to do our coding and testing. Finally, at some point, we reach our production release, and then the system is released to users. And after that point where I was, you had no access to the true system. Actually, the computer our users used was on our site, but we didn't have access to it. Only the division headquarters in Denver had access to be able to change things on that from the computer side, from the IT side of the operation. We never logged onto that computer or anything like that. All right, so, well, in maintenance, there's a number of different activities. It's possible that we forgot something or we had an error of some type and we didn't find it in testing. I guess maybe you've even found some errors like that in programs you've used. Most of the maintenance is adaptive, meaning that there's new business requirements, new business rules that have occurred, and new processes that have to be integrated into the business. And so those require additional data, and then that means that we have to update our system. Well, there's lots of tools to support the system development lifecycle, computer-aided software engineering tools, and they're really interesting, really productive. Some of them can even, once you're done, if you do a careful job of specifying your attributes, they'll give you the ability to say if it's a character or if it's an integer or what type of data, and it'll actually generate a draft SQL, create table statements, if you're patient enough to put all your information into your case tool. It's worth some time. We're not really doing enough in this class, I think, to warrant learning the tool. That's why we're using Visio, which is not a case tool. It's really just a drawing tool. Well, one of the things you have to remember is that the view of the users and the view of designers are different. And what I want is I want you to be able to be a designer, but also be able to speak manager, right? Users and managers, they are are focused on the business. They're not looking at the system. If you imagine, what are they looking at? What is in their field of view? What's in their field of view are the problems and how to solve those problems necessary to enhance growth and future profitability. Right? That's their mission. That's their job. So they're not focused on the system. The system's like in the background of their view. But for us, of course, the system is in the front ground of our view. Right? And we get locked on the system and on stuff about how the data is structured and accessed, but that doesn't matter much to users. But our view is a view that users really will never really understand. And so it's our job, and this is the key point, to speak manager and to be able to translate what we have to know about the data into stuff that's important from the manager's perspective. The more important thing, as opposed to explaining to what we're doing to managers, is making sure that we understand what managers really need, right? We're able to speak enough of purchasing, enough of manufacturing, such that we know what their true needs are. And that is the key idea, right? There's a difference in perspective, and it's our job to overcome those differences. Well, so the database life cycle is very similar to the systems development life cycle. It has the analyze the problem part of it, called an initial study, and it has the design process where we create the conceptual design and then buy the software and implement the tables. Then it had or design the actual tables. Then we go into implementation, then a testing and evaluation phase before delivery. And if you think about it, there's a parallel process between the systems development life cycle and the database life cycle, right? You're starting here in the systems design phase of, well, I would say more in the systems analysis phase for the database initial study, because that's where you're creating your logical, your conceptual diagram, your ER models and things, right? So there's a sort of a parallel between the upper parts of this diagram and the lower parts. Right? Understanding the problem and things now, you might argue that the conceptual model here sort of might go up here, right? But the idea is that you're in the analysis phase, you're getting the requirements, you're understanding the data that needs to be worked on, and then once you really understand it, then you're moving on into the design and then implementation phases. And of course, before you can do any coding, you have to have your database implemented, because your code is going to be accessing database tables and things, and you want that right set from the beginning. Well, the database initial study, I think, is one of the more important parts, and the phases or steps in this activity are analyze the company's situation, right? You need to know what they're trying to do. You need to know how they actually are trying to do those things. And then you have to know something about how they're organized, right? The systems person is able to understand the business from all these perspectives, and that's a increased value on just being able to understand the computer parts. Of course, we need to understand the computer parts, but I think the higher value is being able to understand and contribute even to the business level. And so our analysis or assessment of the business is what leads us to a definition of the things that the system has to do, that have to be incorporated into the database. What are the problems they're having with their data? What do we need to do to give them the proper data? Data that has achieves their objectives, has a proper scope, and includes everything that they need. Well, so it is this looking at what the company really does, understanding their mission, looking at their structure, saying, how is it? Which transactions are generating the most revenue in this organization? How are those transactions supported by our database? And those kinds of issues. And so it's all about saying these are the these are the issues, and these are how they can be addressed. And some of this happens just at a more of a narrative, a descriptive level, until it can be transformed into parts of our ER model and our user requirements. One thing that has gotten systems people into trouble in the past has been that it's users that really are the most important people in our system, because if they don't use our system, then our system fails. And so we need to be sure that we align our activities in the system that we create with what the end users need to accomplish and what they imagined was going to be the system was going to do, or maybe even look like or perform like, right? Because if they don't like it, then they won't use it. And so there's lots of things that we want to do, and we want to always keep the user engaged and feeling at least like that their issues are always being addressed. Now, some of the more interesting things is when you have systems that interface with other systems, and of course data sharing now is a very important aspect of many different systems. Well, when you're doing these systems, you want to only do the scope that is needed by the user. That has been a problem in the past where people have made systems that are not exactly just limited to the requirements, because with just a little bit of this and that, you make a much better system with much more capability, more general things like that. But the point here is those projects have failed in the past, and you need to only do what is really feasible and what is really needed. Right? We are to be responsible stewards of the organizational resources that we've been provided to create the system. So we really need to be careful with how we, with the activities we do and how we spend our money, that we don't do more than is really needed by the users. Well, here's this idea of how different perspectives exist. So sometimes you have a situation where here we have this one thing in the world, and in Department A, they give it one name, and Department B another, right? So they are referring to the same thing with different names. Here we have people in two different departments are have two different things, but they give them the same name. You can see that this is going to cause confusion in the organization. And I can tell you that trying to work these things out between departments is very difficult. It's almost always easier just to give each department its own thing, and then to try and make them resolve some issues. Well, like here's a little example. So the payroll department wants to keep the professor's Social Security number as the key for professor, but in the systems department, Professor Num is a fine key, and so interesting. They also store the phone differently. The payroll department includes the exchange. The systems department necessarily assumes the exchange. Note that the payroll department assumes the area code. So you can see that these little subtle differences between the data requirements for different problems or different departments, different business functions, makes for an interesting perspective. Now you can see it wouldn't be too hard to convince the systems department to use the phone attribute from payroll because, hey, it's just a few more characters. And it's possible that some of our professors live in different exchanges. Highly likely, actually. And then you can see why payroll wants to use the Social Security number for professors, because they have to handle their tax withholding and payment and those things, and that's the number they need to make those, to perform that requirement. But and you can also see why the systems department might want to use SSNs. You know, back in the day, it wasn't such a big deal, but now everybody is very concerned about revealing their SSN, and so unless it's a real reason to use it, people try to stay away from it. And so here, this just gives you an idea of the complexity of working with data that, you know, I know it seems unnecessary in things, but it actually occurs, and you need just to be aware of it, and that your goal is to resolve all these things, right? We never want to have one entity with two names or two entities with one name. Those things make no sense. At least try to get the organization or the departments within the organization to at least try and resolve it. Well, so the database design is where we do a final product check. We're trying to come through here. We know all the operations. We know what we have integrated all of the different requirements, and we think we know everything we have to do. We have come up with all of the entities and the attributes, and so now we're ready to implement this data component and write the program. And so here we have some activities that are associated with our design process. And of course, I guess I'm getting to be broken, but these are the most important to me, right? Where we're doing understanding our data and our requirements, doing our ER model, and then verifying our data model, making sure that this model that we create is a true solution to the problem. You know, and you can see that when we get in here, right, not only are we drawing diagrams and things, we're also thinking about the reports, what kind of queries we're going to use, and all of those types of ideas. We want to make sure we can say we've solved the problem. Well, but after we've done that, now we're moving away from things that are purely conceptual and logical. Now we're moving down into this, or things that are truly just abstract and conceptual. Now what we need to do is translate this beautiful model that we created into something that will actually be an information system. And to do that, we move from this DBMS and hardware independent perspective and to start customizing into the DBMS. We create the tables the way the DBMS requires us. We use their referential integrity. We understand, we figure out how their referential integrity maintenance works. We understand it and employ it. We are sure, again, that we're meeting all of our user requirements. That is a big issue. And then finally, we would get down to physical design. We say, what tables are we going to have? What kind of security groups and are we going to implement? And then finally, what kind of criteria are we going to use to know when we have a problem with our query results? Well, one of the things that we do is load the database, right? Like in our Department of Energy Power Billing database, we had the requirement to be able to go back and recreate a bill any time within the last 7 years. So we had to be sure that we loaded enough data to be able to do that. But what that meant is that we had to load 14 years of data, right? Because we had to be able to rerun a bill from the very first day of 7 years ago. And to be able to estimate that bill, we would have to have 7 years of prior data. And so it was a very interesting process of what we had to do to really load the database with all of the data necessary to start testing our program. It was a very involved and complicated process. But this is one of the things that I didn't realize how long it was going to take until we did it in this system. Even though we did unit testing all the way along as developers, and sometimes even tested each other's applications, it's very difficult for people on the team to do the testing. So we were fortunate to be able to have a couple of helpers who did a lot of our testing. And basically it's a process of trying to do the work it was intended to do and see if there is a problem. And then usually it's just some sort of minor programming or a minor problem that we encounter, although we usually catch most of those in our unit testing and system testing processes. Well, if things don't run fast enough, then we can do some things. We can take a look at our DBMS. We can do like we did in Power Billing. I mean, it wasn't really slow, but it wasn't fast either. But it was good enough, and we didn't have any complaints. But we were worried that if over time it would get slower and slower because of the chaining of data from month to month. At some point, you run out of the contiguous space that you reserved, and then you start chaining files, and that makes things run slower. So what we did was we wrote a routine to make sure that every month we had enough empty contiguous space in our files for each table, so that we could, the next billing cycle would not require any of them to chain. And so our system ran the exact same speed every month because of that decision. There was always enough space in the database to expand to the next month. Well, security is really a big deal in testing, right? And an audit trail really is part of security. I mean, you want to be able to know how something that was changed incorrectly, what was the path to it that changed it. So there's a lot of key ideas on here. You want physical security. You don't want anybody to get to the server. You wouldn't believe how bad people are in password security. I hope you don't have your password taped to the bottom of your keyboard or something like that. One of the things you're going to be seeing more and more of is disaster recovery plans. Now, even since we were part of the government, and even in the 80s, we had detailed disaster recovery plan, including who would go to the recovery site, and where the recovery site was. And I think ours was in Dallas, but it was it's more and more becoming a part of every system operation about how you're going to be able to recover. Well, operation is when the users are using the system and the actual doing the work that the system was intended to do. At this time, the developers are not part of the user's perspective very often, unless there is some sort of problem. And it's possible, but we try to uncover as many as we have. If we have performance problems, we can do things like load balancing or adding memory, throwing out more hardware at it or something. But we can't really make any changes to the actual code and things that are in operation. That's a very highly controlled process known as configuration management, and it's like its whole own discipline. Well, occasionally you'll have some maintenance to the database, really, right? Where you have to change tables or things like that, where you may need to adapt to some new type of business requirement or something, or some change in levels of access. But one of the most important things going on is the backup process. It's a good, serious backup process that enables things to be corrected whenever a disaster occurs. And a disaster will occur. I mean, although that sounds kind of negative, the disk will fail, or a computer motherboard will fail. I guess that's not as disastrous as it's sounded, but the idea is that when we have proper backup, we can easily take corrective action and restore our database to integrity. And so, but we have to specifically plan to be able to do it. And then we have to continually execute to allow us to be in a position to do it. We have to know what we're going to do, and then we have to maintain our ability to do it. It's a very, very important process. And there's a number of levels of different backups that the book talks about, whether we have full backups and just backup what changed that day. We basically had a full backup every month and incremental backups every week. But without backup, your system is very vulnerable. Well, there's a number of things that can cause us to fail. And, one is the operating system or DBMS software fails. Many more, that's of course very rare, should never happen. The common thing is we're going to have a computer or hard disk fail. And if we're in sort of a server rack kind of world, those things need to be able to fail without any serious issues. And the DBMS helps us work through that. It's the tool that helps to be sure that whenever something fails, we have the ability to recover. Of course, that depends on making sure we have the backups that give us the information to be able to recover with. Sometimes there's a programming an exception. If there's an exception and it's not caught, and that's really bad. There ought to be a design that allows the catching of all errors, even if those errors are undefined, such that the user never aborts. Well, with transactions, the problems that you have is there's some that don't occur that often, and they might interfere with other transactions. Maybe they don't occur that often, they weren't coded perfectly correctly, and so their locking processes are a problem. Maybe locking things from themselves in a way that causes a deadlock or something like that. And then finally, we can have some sort of disaster, and from that we'll need a... Well, now I'm going to talk a little bit about how to take our conceptual design into a physical design. And it's a very straightforward process. There's no mystery to it. It's just a step-by-step sequence of activities that we do for our database design. Our program design has a little more art to it, and we're not going to talk about that today. And I think you covered that, functional decomposition, those kind of ideas in software engineering. Well, so in data modeling, we make this ER model. It is our semantically correct in terms of the real world. Remember, we're trying to make a model that mirrors that world because it's going to give us stability and flexibility. It shows that we have a good understanding of what the business is doing. We should now know all the data, all the entities, all attributes, and we have completely determined the solution to the problem. That's what it means to say we are done with conceptual design. If we've reached a conceptual design, that means we know everything in terms of data. We have a solution to the problem. And so basically it's this idea that we're going to take in these information sources and we're going to then use our knowledge and our design tools to transform them into an ERD, and that's going to be our model. And then we're just going to keep going around until we feel that we have the complete ERD. And what happens is you keep getting information. You have the data flow diagrams, you have the functional decompositions, you have business rules and things, all the things that you learn from the user and from the existing system and from the problem domain and from your analysis. And all that feeds into your ER diagramming, and then you use that to create the ER, create and validate the ER diagram. So what happens is, in the beginning, these things, there's a whole lot of stuff to do, but after a while they start slowing down, and then it comes a time when you see that there aren't many changes occurring, and that's when it eventually get to where there are no changes for a little while, and now you find that this is your final model. But it takes a little while to work through all these things, and of course it all depends on the size of the system and that kind of stuff. Well, there's two types of general sort of overview types of design. And one is the sort of centralized design where you make a model of the whole problem, and then if there's any things that are particular user views, you break those out. So rather than so you make the entire model, right? You don't think of it as pieces. It's centralized, and then you pick out pieces of that model for individual user views and work from that perspective. A decentralized design takes more of a individual department type view. Here we have engineering, purchasing, and manufacturing. And so each area is sort of analyzed on its own, and you determine what kind of views and processes and integrity constraints they have. And then you bring them together in this aggregation step to develop your conceptual model. And, this to me is more common type of perspective. Usually we're not doing a system for just one department, but if we are, that makes it easier. But it just sort of shows you that the one of the things that's not shown here is there's going to be a looping process here too, or iterative process here too, so that you're going back through on the users and things. All right, but as conceptual models, when we come out with it, now we're really ready to do something. Well, how should we go about this creation of our conceptual model? Should we start with all of our attributes and then work our way from the bottom of all the attributes and then work our way up derive, to abstract up to the conceptual model, to generalize from attributes to the conceptual model? Or should we think in terms of a high level and then drill down and come up with a top-down process, like identify all the entities first, or identify the major data elements first, or large transactions first? Well, I think we sort of fall over here, don't we? Right? Because we're using an ER model. I mean, maybe I guess we could be going inside out, but you know, we're identifying entities, and then from those entities, attributes and other entities, things like that. So I think we're probably more top-down. And other techniques like object-oriented analysis and design, you know, sometimes call themselves middle-out, right? So that you can work on any part of the problem you want and still be able to work through all the problem without causing issues. You know, one of the things is with the waterfall model that we talked about a few minutes ago in the systems development lifecycle, if you make a mistake in the analysis part, it trickles right on down into the design part, and then down to the design part into the implementation part, so that you end up having, you know, a mistake sort of compounds itself. And that's part of what the OO approach was trying to get away from, was trying to make each individual thing stand alone, right, where it has all of its own data and process in one element. And it's worked pretty well in many situations, and so that might be called a middle out versus a top down and bottom up. But I'd say using the ER models, we're probably coming in at a top down perspective. Well, this idea of validating or verifying our ER model is really critically important, right? We have to be able to be sure that we have our model, right? And so coming in from our database initial study, we have all of our analyst views, our rules, right? We would even have some of our reports, right? And well, we'd have all of those, as much information as we could get, all in terms of all the possible entities and attributes we have. And of course, we made our initial ER model. And this little process here, there's an iteration too, where you are going to be going back and forth with that model. Right now, once you have this model, then what we want to do is come through and verify that the model that we have is suitable for meeting all the processes and transactions that we have. And that's what the verification process or verification is about, where we say, okay, here is a use case, and this use case has this interface. This interface has these attributes on it from these entities. Are those attributes and entities in our model? If you follow me, you see how detailed this is, how it's very precise, but it is still on a conceptual perspective, right? It's not, I mean, we are working to solve the problem in a way, but we are still not writing any code or any SQL to create tables or anything like that. And so, you know, the process here is to, you know, iterate through here, iterate around here, and come up with a final ER model that is complete and correct. Once we have that, then we're ready to move forward into the design phase. Well, so here's some steps we can use to guide us on using our ER models. And, you know, I think these are all the things that we've been talking about all semester. I'm not going to go through them in any real detail. I would say, you know, I guess you wouldn't be surprised to see me point out that the important things are the primary keys and the foreign keys, right? So because that's what's going to give us the structure that allows us to use our SQL and all that stuff on down the line. Well, and I guess would be my other big thing, right? We got to make sure that all of our end user requirements are satisfied, right? That validation process is really, really critical, because if we get it right, and if we got it right on our analysis and we know what all the users have to do, and we get this right, we're going to be really a long way toward having our system be right directly off the start. And that really frustrates users if right out of the box your system doesn't work just right. Well, we should know all of our requirements for all of our attributes. We know all their data types. We should know all their domains. We should know where they originate. We should know where they're used. We should know what the default value is for every attribute. Right? It's just part of making a good design. Well, we can use normalization. I mean, it's not going to help us that much, right? Because we already know that our model's in third normal form, right? If it isn't, we haven't completed our ER modeling process yet, right? All of our business rules, everything we know, right? And that's the beauty of an ER diagram, is we can put everything we know onto it, all the constraints that we've identified. Remember how I want you to label both directions of your relationships. That's because there's information that you've learned about the world that is now in the model. And we can use that model to help us communicate not only among ourselves, but we can also use it to communicate some with users. But when we get this correct ER model with all this augmented information, it makes it really straightforward to convert it into the database. Well, verification, of course, is the most important step, because this gives us a chance to stop and check and make sure that if we made any mistakes in our analysis phase, now we can circle back and see that we can fix any problems. So now is a good time, right, before we've made any tables or done any coding, to stop and check to see that we have the ability to do everything, to meet every user requirement, that we have an attribute in our database for every attribute on every report and on every screen, from every use case defined as needed by the system. And here's a summary of how we might go about verifying our ER models. I'll just suffice it to say that we need to know, right, for every transaction, right, for every update, insert, delete, query, report, that we have the proper data in our model. And that's as simple as it is, right? I mean, just have to check. In the same way that we said we had to check every attribute of every entity to identify its functional dependencies so we could know if it was a normalization violation, we have to do something similar here, except what we have to do is every transaction, every insert, update, and select that processes against our database, we have to know that it has the right, that we are giving it the right data that it needs. And so this is sort of the simplification of our this verification process, right? You're just going to iterate around and around and around in here until you're finally happy. And I would say that, it's all us that decides when we're happy. Right? I mean, I guess we could have an interaction with the user that could guide us one way or another, but it's our model. It's our job to make it right. So what we when we are making changes, we are just matching more closely our understanding of the world. And that's why it doesn't change much over time. Eventually we get to where we really do understand the world. In most cases, it's not actually that complex. And so once we really understand the world, right, then all we have is the process of negotiating what model most accurately represents that world. And so once our understanding of the world stabilizes, our model stabilizes fairly quickly afterwards. Well, in programming, we have the ideas of cohesion and coupling, and I'm sure you've talked about those in software engineering, so I'm just mentioning them here briefly, with the idea that when we are making a program module, what we want modules that are more cohesive in that they use subroutines and functions that are part of the module more than they use subroutines and functions that are part of other modules. And so that's the idea of cohesion. And that's where object-oriented classes are said to have very high cohesion, because most of the methods in a class use only other methods in that class, rather than a bunch of methods from other classes. And so that idea is important for making your programs understandable. And coupling is the idea that every program makes a call to other functions or subroutines. Right? The fewer calls you make, the simpler your program, or the fewer things you are connected to, the simpler your program. And so, but there can be a trade-off, because programs with very little coupling can be longer than shorter programs with more coupling. So what we want are modules that are fairly loosely coupled, and highly cohesive. Well, distributed database design is associated with deciding where the database will be in relation to the users. Sometimes we just have one big centralized database and it works fast enough for everybody and we don't have to do any distribution. It'd be interesting to know what is Amazon's distribution strategy. We ought to on their data, right? If you have a big enough server farm, then you can keep all your data in one centralized database. So, but if you decide that and almost always for performance reasons, you need to locate data near users, that's called database fragmentation. And so, depending on how you fragment, right? Like say you wanted to keep all of the Social Security records for Alaskans in Alaska, because they're the only people that ever check the Social Security records for people in Alaska. It would make it a lot faster, and it wouldn't hurt anybody else because nobody else is ever looking at those records. So let's keep all of the rows of the Social Security, the taxpayer table identified by SSN, taxpayer ID. Let's keep all the rows for that table in Alaska, in Anchorage. That would be what's called horizontal fragmentation, in that you are taking the rows and putting them in different locations. Vertical fragmentation is the idea that you put one column in one location and another column in another location. And it's always because the users in one location need different data than the users in another location. Maybe marketing needs the customer address, but engineering just really doesn't care. They just need the phone number of the contact. This is a really interesting topic, I think, and I think we have it on our agenda for Chapter 12. Well, the DBMS is really critical in coming up with a successful system. And today I think you'll see people not taking too many chances with their DBMS. They'll go with Oracle or SQL Server or DB2, really, really solid products with lots of features and installed user base and lots of positive things. So you won't probably be involved in deciding about purchasing for a while, but these are the kind of things that you want to make sure you address. You want to know what kinds of tools and features does it do. You know, I like thinking about their underlying model, right? Where in Oracle, it's very simple, right? Once you understand their systems catalog tables, it's like, hey, this is logical. It works. I can see how what they're doing is they are storing their catalog in a relational way so that they can process it with their relational tools. In other words, they believe so much in what they're doing, they're applying it to do what they want to do. And I think that's a good feature. Portability is a big deal. That's, gives us the ability to go from one vendor to another. That's mostly in the terms of SQL portability, which is high. And of course, there are going to be hardware requirements. These usually DBMS servers are substantive. Well, logical design is where we take this conceptual, beautiful solution that we have to the problem, and we start mapping it into the DBMS, and we're trying to fit it right into whatever decisions we've made. Right? If we're going to go with C, right, well, then we're going to be making some decisions in that way in terms of what our design, our functional decomposition of what our design is going to look like. And but this is where we really start to lose our independence and move from this totally logical, conceptual way of thinking into implementing what we have. And like, we're no longer really doing any changes to our entities or tables or attributes or things. Now all we're doing is really just specifying them, if anything, in a little more detail and getting ready to create the tables. Well, we want to make sure that all the constraints that we've learned about over the time that we've been collecting our user requirements, developing our use cases, all of our other study of existing systems and other activities, we've learned a lot about every attribute. We got to make sure that we've saved it somehow, and that when we are ready to move into creating the systems, we are able to quickly evaluate each piece. We should already have all of our individual entities evaluated for normalization. So really, if we're going to come back and say we are in at least third normal form for all of our relations, the only thing we can be doing now is coming back and looking to see if we have any fourth normal form or other things that could be either disaggregated or combined. One thing is security needs to be thought of as a design principle. It needs to be designed in from the very beginning. You can't just sort of tack on your security at the end. And that's something that we used to try to do, but now it is important to think about. And although the mechanisms for implementing security still haven't changed substantially, it's just something that not only do we need to think about it in development, but also in all of our phases of finalizing our system. Well, the ultimate is user requirements. We need to know, the user needs to know that every requirement can be satisfied by our design. And that's why we go to all the trouble of making detailed user requirements, so that we can go then look through all of our model and know how that requirement is satisfied. And we just have to know, we just have to have a requirements tracking process, so we know all the requirements that are in our system, and make sure that we satisfy them. I knew a person once who made a fantastic living asking one question, right? What user requirement was satisfied by this design feature? And, everything has to have a home, right? You can never have any user requirements that aren't satisfied, and you shouldn't have any design or system features that aren't associated with some user requirement. Well, this is pretty much a straightforward process, right? So what we're doing is we're just going to take the entities in our ER diagram and the relationships in those diagrams, and we're going to map them into tables in the database. Right? We're already normalized, so when our tables are created in the database, they will be normalized. When we look at our integrity constraints, we'll build those into our create table statements. And we'll bring in first our entities, then our relationships. Well, now when we move into physical design, now we're just using the DBMS to implement all of the things that we determined we needed in the logical design. We said we need these tables. Now we are creating them and making decisions about what types of storage and things we're going to have. And when we make our distributed systems, it's more complex because it's just multiple instantiations of whatever we decide. Right? If we decide to fragment the customer table such that the customers for China are in China and the customers from US are in US, then we just have to have the hardware and the facility in China to run the system. It's just in the same way that we'd have to have one here, right? But once the method is set, it'll be used the same way in both places. Well, there's really three overall steps. Define how the data are actually going to be stored. Check and review your integrity and security approach, and then evaluate your performance measures. What we do, or what we have to do as designers is say, what's the expected volume for every one of my user interfaces? Every one of my user interfaces or reports or batches that my system has to manage, and then how often and regular are those patterns or those volumes going to occur. So that gives you a feel for what's really going to be, how the data is going to be sort of pulsing through the system, so to speak. In our billing cycle for the Department of Energy, it always seemed like the last week of the billing cycle, the billing folks were going nuts, right? And it was always because they didn't do anything for the first 2 weeks, but that's just beside the point, I guess. So, based on the max throughput you have to handle and when those things are going to occur, that drives the type of storage you have to acquire. It sometimes has input on what indexes you'll create, right? Like if you really know you're going to have a high volume situation, you might deliberately create an extra index that is going to cost you time at insert, but it's going to give you the ability to resolve some commonly occurring high volume query using only indexes rather than using the actual data records from the file. And that's going to make things go a lot faster. And of course, the optimizer will be able to know whether it can do that or not. But if you don't have the index, it won't even be able to do it. Now, today, I guess it might be smart enough to suggest the index, but you know, I mean, we've sort of created the system by describing everything it has to do as use cases, not necessarily prioritizing any one use case over another in terms of how much data it was going to provide to the system. But now this is when we are thinking about that, because it's going to determine for us how we're going to manage a lot of the actual hardware and how the disks are going to be organized. Well, security roles are really important, and it's a separate task. It was for us. We didn't have developers setting security for other developers or anything like that. It was always a manager on the government side who managed all the security groups and things like that, and keeping these things right and testing them. That's something that I think sometimes falls through the cracks, is testing the security groupings. That when a person is logged in a certain way, they can't do some things, and they can do other things. And to make sure people with multiple logins can't do one thing when they're logged in the other way. Like if you have two logins, one is a manager and another is an employee, and as a manager, you can do some things, but as an employee, you can't. It needs to be sure that those systems are tested. That there's just different security controls are tested. And what we usually do is we have groups of users. Some groups of users had update or insert. Nobody ever deletes from our tables, and other users only have select permission. Well, I know you might think I get carried away on this idea of performance, but it's important. If your system doesn't perform fast enough, then the users won't want to use it. And even you can say, well, they have to use it because this is the only billing system they're going to have. It would be a problem if it wasn't fast enough. There's just no way to get people to use slow system and not continually complain. Well, our performance, we can add different media, throw some more hardware at it. We love to do that. Usually, if it's something that we can fine tune in the queries, there's not that often that many things that we can do. But this is where, if you really have performance problems, you might need to denormalize or something like that. But you don't know that until you already reach this implementation phase, and really an operational phase. Well, tonight we talked about what is a system and what is the systems development life cycle. The database life cycle and how it fits in with the systems development life cycle. How there's different views of the world by business managers and database designers, and it's our view to understand their world and to be able to speak their language. Not so much vice versa, where we would want them to understand our language. And I think it's just not feasible, really, to expect these folks to learn what we know, because they have responsibilities that are business focused. The data in the background, the data and the systems are in the background of what they do. They are supportive of what they're thinking about, whereas they're sort of in the foreground for us. So we have to understand that, and we have to work with them and be able to speak their language. That is, listen to what they're saying and then translate that into data, and then explain that to other people, programmers and analysts on our side, in a way that they understand it from the design side. Well, there's conceptual to physical design. We talked about how to iterate through a process that ends up with a implementation of our physical database. It's just a direct mapping from the entities and attributes of our conceptual design, including all the information we've learned about them throughout our user requirements and study and initial analysis. And so the testing and the mapping of our entities is really straightforward, or the mapping of our entities and attributes to our DBMS is straightforward. Testing, including security and ensuring our performance, are also critical. So that's all I have for today. I hope you have a nice evening.